Hello everyone, welcome to our first video in AP Physics C, Electricity and Magnetism. This one's going to be talking about electrostatics, which is this pretty big unit that covers electric charge and field and Coulomb's law and things like that. We got electric flux and Gauss's law, and we've got electric potential, energy, and potential. So it's like three big main chapters, all in this one unit. So it's going to be a pretty long video. I'm going to try to condense the content review as much as possible. And I handpicked a set of 9 problems that reflect probably the most challenging types of problems in this unit. I skipped some of the conceptual ones, which you should be able to like reason through. And it's mainly like the math heavy problems that I have for you. So without further ado, let's get into the content review. So let's start with what is electric charge. Electric charge is basically a fundamental quantity, just like how mass or temperature and things like that, those are fundamental quantities. So is electric charge. It's just something an object can have. And so you either have positive or negative charge. And some people also say neutral, but neutral just means no charge. That's not a type of charge. It's just you can either have positive or negative charge or zero charge. And you probably already know this from like childhood science, but like charges repel, unlike charges attract each other. So a positive and a negative attract each other. A positive and a positive repel. A negative and a negative repel. Additionally, if you have a neutral object, then a charged object attracts a neutral object. And I'll get to why in a second, but it's just important to keep in mind. Just like other quantities, charge is conserved, so the total charge in an isolated system is constant. We are going to be using protons, neutrons, and electrons to discuss charge, because protons are positive charge, electrons are negative charge, and neutrons have no charge. So it's mainly going to be protons and electrons. One important thing to note is that electrons are tiny, much tinier than protons, and so usually you're going to be talking about electrons moving and protons staying where they are. And so a lot of the conceptual stuff here has to do with the electrons are moving, and that's what causes charge and current, which we're actually not talking about in this unit. That's next unit, or maybe the unit after that. Anyway, back to this. The fundamental quantity of charge is an electron. So you represent that with E, and you probably should know what the charge of an electron is because it's just referenced so many times. It's approximately 1.602 times 10 to the power of negative 19 coulombs. Now, coulomb is the unit of charge of an, just the unit of charge. And so this is a very tiny value. But what that basically means is that a coulomb is very large. You're probably not going to encounter many objects with 1 coulomb of charge. It's always going to be very tiny. And yeah, that's why electrons are mainly responsible for like atomic structure and circuits and things like that, because protons are just too big and heavy to move. It's about 1,000 times heavier than an electron. We've got 2 types of materials that we're going to be talking about: conductors and insulators. Conductors are where charge moves easily. So if you have like a bunch of protons and a bunch of electrons surrounding them, in an conductor, all these electrons can move wherever they want. So you can end up with all the protons on one side and the electrons on the other side. In an insulator, charges can't move that much. So instead of moving all the way to one side, what you'll get is all these protons here, and the electrons move to one side of that atom. And so there is this partial charge that is on this object. Here, you got like completely polarized, split down the middle. Here, you got some negative charge on one side and some on a positive charge on the other side, which is weaker than a conductor, but it still shows that you could charge an insulating object. And then you probably also learned how to charge like through induction and things like that, which I won't really go through because we don't need to. It's not going to be the problems, and you probably could just read the textbook for that kind of thing, and it's also probably not going to be on the AP test very much. Anyway, moving on to Coulomb's law. So Coulomb's law is when you have 2 charges in most cases, and they apply a force on each other, kind of like the law of universal gravitation by Newton. It's very similar to that, actually. So let's say you have 2 objects. Q1 and Q2. So Q is the symbol that is used to represent charge. They are a distance r away from each other. Coulomb's law basically says that the force between them, the electric force, is equal to k q1 q2 over r squared. What's k? It's just like how g is a fundamental constant in the law of universal gravitation. K is a similar constant here. And so you have k equals another set of constants. It's 1 over 4 pi epsilon naught. Epsilon naught is another constant. The reason why we need both of these is that epsilon naught is very important, like later on in some advanced physics, and k just makes it look better. If you want to write the full formula, it would be 1 over 4 pi epsilon naught times q1 q2 over r squared. So that's the formula for electric force, Coulomb's law. Again, the direction of the force depends on the types of charges. Like charges repel, unlike charges attract. Okay, moving on to electric field. Electric field is just like force, a vector quantity, and this time it's force per unit charge. So it's equal to just the force over the charge, and that basically means, let's say you have like a point charge here, and if any other charge comes into its electric field, then there would be a force between them. What an electric field and force have differences between is that you don't need that other charge for there to be an electric field. Every charged object has its own electric field, and what I'm doing right now will make sense in a minute, but no matter what, if there's another charge or not, there's going to be an electric field here. Now, if you have another charge enter that, now there's a force between them, and that exerts its own field, which like comes into contact with this field, and you get these electric field lines, which again I'll talk about a bit later. What the direction of the electric field is the direction that the electric force would be if a positive test charge were introduced into the field. So if you have a positive, like a proton in the middle of an electric field, and you introduce a positive test charge, then they're going to repel, and so that's why the electric field points outwards. If you have a negative, like an electron in the middle, it's going to come inwards, because if you add a positive test charge somewhere, it's going to try to attract. And so that's basically what these arrows represent for electric field. Now you have this equation. You also have is equal to kq over r squared, where q is like the charge you're focusing on. Here, it's basically just, these two are not the same q, by the way. I might want to turn this into uppercase q, because just to indicate that they're different q's. This is the q that is producing the electric field, the charge that's producing the electric field. This is a test charge. And so if you did have a test charge, then the force between them divided by the charge of the test charge is the electric field. If you didn't, then you would just use this formula, which is kq, this q, over r squared. Electric field is a vector quantity, so when you have multiple together, it's a vector sum. And so let's say you have three different objects here. There could be an electric field going out this way, coming in this way. Let's say there's a negative object, negatively charged object, and then going out again. And what you would basically do is calculate the electric field of each one as a vector and add them all like through a vector sum. And then what I was talking about before, which is electric field lines. Electric field lines are a graphical representation of electric fields. And so if you have a positive and these arrows coming out, that's technically kind of like an electric field line. Now, when it gets interesting is when there's multiple charges. So let's say you have a positive and a negative. Well, it's going to be coming out of the positive, and it's going to be going into the negative. And so putting it together, you would basically say, well, it goes from the positive to the negative, from the positive to the negative, from the positive to the negative, and so on. And these also go out, but they go out of the field of view, so you would probably just do something like that. And then, from the positive to the negative, from the positive to the negative, like that. And you would use arrows to denote which way it's going. If you have two of the same type, let me put them farther apart, then they repel each other. So they're going outside for both of these. And so they just continue going outside. They don't go near the other one. They kind of bend outwards a little bit because they also don't want to go to the other one. So in the middle, you have this point that is completely like there's no electric field there. So that's pretty interesting. Now if you have negative charges, it's the same, but it's coming inwards. And then the last topic for like this subunit, which is electric charge and field, is electric dipoles. If you have a dipole, that's basically two charges, a pair of electric charges of equal magnitude but opposite signs. So you got a positive here and a negative here, and it has a quantity called the electric dipole moment, P, not to be confused with momentum, which is also P. That's equal to QD, the charge on one of those times the distance between them. And there's a few formulas you should probably know for this. You can apply a torque on a dipole by applying the same force. So it probably attracts the positive charge. If you have like a negative charge here, it attracts the positive this way and repels the negative this way. And so you get a torque, a net torque. And so the torque is equal to that moment times the electric field that is imposed upon the dipole moment, upon the dipole. You also got a formula for the potential energy, which is equal to negative times this, and this is the dot product, actually. This here is the cross product, because that is how you calculate torque. We went over that in rotation. This is the dot product, and so it will be a little bit different. All right, that was it for the first part. Now we got a lot more to cover, namely electric flux and Gauss's law. So let's get into that. So what is electric flux? It's a measure of kind of like the flow of the electric field through a surface. And so if you have like imagine like a solar panel or something here, and you got arrows representing the electric field going through it, then you got an electric flux. What is the formula for the electric flux? Well, it's represented with this, with an E, because there's also magnetic flux we'll talk about later this year. And that's basically equal to the electric field going through times the area. Now, there's a little bit of a difference, because if you're coming it at an angle, that makes a huge difference. And so it's going to be that times the cosine of the angle between them. Sometimes it's represented with a different angle symbol like this. It doesn't really matter. So if you have this formula, that is the electric flux formula. It's not always written like that because sometimes the electric field isn't constant. It's non-uniform. And so the main way of writing it is the integral of E times dA, which basically means it's the dot product of electric field through a small portion of area, an infinitesimally small portion of area. And the reason why area gets vector is because it's nice to think of it as a dot product, and a dot product requires two vectors. And since area is just a quantity, a scalar, what you can do is to ensure that you also get that angle portion in, the area vector has a magnitude that is equal to the area of the surface, and its direction is completely perpendicular to the surface. It's the normal vector to the surface. And so that's going to be your formula for electric flux. Now, what is Gauss's law? Gauss's law basically relates this to charge. And that basically says electric flux equals this, which is equal to the charge that is enclosed within like a volume over epsilon naught. So epsilon naught appears a lot of places. What does this mean? So if you have like an irregular shape like this, you might not be able to calculate dA, which is the surface area, because it's irregular, but you do know that there's some charge here. That's all you need to know to calculate the electric flux. What that also means is if there's no charge inside, but there's a charge outside, that means there's no electric flux. That means it goes through one side of the surface and then goes out the other side. So there's no net electric flux. If you add it inside, there's no way to go except outside. Well, if it was a negative charge, it'll go inside, negative electric flux. But still, it's all going in one direction, so it doesn't cancel out. Yeah, and that's also another way to relate electric field and enclosed charge. And I'll get to some examples of this later on when we do the problems. You're also probably going to be asked to calculate the electric field of certain continuous charge distributions, is what they like to call it, like a ring or like an infinitely long line of charge. And so this comes in handy a lot. I'll just give you an example. If you have, let's say, a conducting sphere with a radius r, then outside the sphere, the electric field is going to be K, Q over R squared. Well, that seems obvious, but that's basically treating the sphere as a point and just saying, okay, it's just the electric field produced by that point. If you're inside the sphere, anywhere inside the sphere, the electric field is zero. It's something called the shell theorem. Basically says that, hey, you might be here, which means you're getting more electric field from here, but it's a smaller area there that you're getting it from. Here, on this side, you're getting it from a larger area. It's weaker but larger area, which basically cancels out. You can do the math to figure it out yourself, but they cancel out, and so no matter where you are inside, it's going to be zero. Also something important to know. And so, yeah, we'll be doing some example problems where you have to actually derive this formula for some more complicated shapes. We'll also be dealing with densities, charge densities. So obviously, you probably know rho, which is volume density. In this case, rho is also charge volume density, which is the total charge divided by the volume of an object. You also got sigma, which is charge over area. That's the area charge density. So this is useful if you're talking about a surface rather than like an entire 3D shape. You would want to use sigma. And then you got lambda, which is equal to this over length. It's the length charge density. So if you have like a line of charge, you would use that. And that's basically it for Gauss's law. And moving on to our third subunit, which is electric potential energy and electric potential. What is electric potential energy? So we talked about potential energy way back when in semester 1. Electric potential energy is just potential energy due to electric charges. We already know that work is equal to the change in negative change in potential energy from before. And so the work of going from A to B, of bringing a particle from A to B, is equal to the potential energy at A minus the potential energy at B. Usually it would be B minus A because that's the change, but remember it's negative change, and so it has to be A minus B. What is the formula for potential energy, electric potential energy? It's equal to, as you probably guessed, KQ1Q2 over R. Not R squared, it's just R. And that's because of this, actually. Work is equal to negative change in potential energy. So you take the negative integral of your force formula, which is KQ1Q2 over R squared, and you do stuff with that. Now, potential energy is not a vector, and so when you have multiple objects, like 3 objects here, you would just straight up add them. It's not a vector addition, it's just completely adding. You find each pair of points, and you find the potential energy between them, and you just add them up. Very simple, or simpler than electric field, I'll say. Then we got electric potential. We've probably never talked about gravitational potential. We talked about GPE, gravitational potential energy, but not gravitational potential. So this is where it kind of diverges a bit. We're going to be talking about electric potential, which is symbolized with the V. You might know that it is voltage. It is the same thing, but voltage is next unit, or whenever we do circuits. Here we're going to be calling it electric potential. Its full name is electric potential energy per unit charge. And it's basically just that. It's U over Q. Just like how electric field is F over Q. Lot of parallels here. So what does that mean for the formula? It's also equal to KQ over R. Similar to electric field in the sense that there's only like the one charge. You only need one charge to have an electric potential. Now, if you have a collection of point charges, then again, just like with electric potential energy, you just add them up. It's the summation of all the V, of all the pairs, of all the point charges. For potential energy, it's pairs, because you need 2 charges to get potential energy. For potential, you just need 1 charge, so you just add up all the individual charges, potential energy. Now, if you have a continuous charge distribution, again, they love that word, it's equal to K times the integral of dq over r, or as it probably looks a bit more familiar, integral of k over r times dq. That would probably make a little bit more sense. I think we do have an example problem similar to this, but don't worry too much about it. You just have to find you convert dq into dr, kind of like what we did with moment of inertia calculations a bit before. We had to calculate like dm into dr to actually make it work. And so you're basically doing something similar with that. You would need to use something like rho or sigma or lambda to get it, to convert. And then also relating electric field and electric potential, the change in electric potential, so VA minus VB is equal to the integral of A to B of electric field times dl. So not dA, which is Gauss's law, it's dl. And so, again, that's a little bit of a similarity, a little bit of a difference. And once again, note that it's A minus B, A to B. That's because of the negative sign that is the relationship between work and potential energy. Okay, equipotential surfaces. So that's basically surfaces where the potential has the same value at every point. So if you have like a negative sign here and a positive sign here, we could draw those field lines like we did before, which are all going in one direction. In this case, it's going from positive to negative. We can also draw the equipotential lines. So these, I'm probably going to use a different color for. They're basically like concentric circles in this case that surround each charge to show like if you have a point on any of these circles, so let's say this point, that's going to have the same potential as this point. Since in this case it's a bit weird because there's a negative and a positive, so it's not perfectly concentric circles. If you just had a positive, it would be perfectly concentric circles. But since you have two charges, you have to also account for the potential you get from that negative sign or negative charge. And yeah, that's why these circles look a bit wonky. And down the middle right here, it's just a line of equipotential. All right. And that's basically it. There's like some niche topics. This is just the broad overview. You might want to read the actual textbook to get a hang of like the more, like also doing example problems and also like the weirder concepts in the middle. But that's mainly it for the content review, which was done in pretty good time. It's now time for the problems. So let's get started. I think I have 3 from each subunit, like I like to call it. And so let's start with electric charge and electric field. Again, I skipped some of the easier ones because 3 subunits is a lot to cover. I originally had some conceptual questions about, charges and like which sign would cause repulsion or whatever, and I also had like a Coulomb's law problems, but that was just way too much. Instead, I'm starting off with electric field because I'm sure you know Coulomb's law, at least from gravitation, because it's very similar to that. And also, if you took chemistry, you might have learned it. And yeah, it's not the hardest topic in this unit, and so that's why I wanted to jump straight into electric field. Okay, what's this problem? 3 negative point charges lie in a line. Find the magnitude and direction of the electric field this combination of charges produces at point P. So we have this point P, and you got 3 different electric fields. And so we're going to have to do that vector sum I was talking about earlier. So this distance is 6 centimeters. That's 8 centimeters. And Pythagorean theorem, that means this is 10 centimeters, as is this. It's a nice Pythagorean triple. This charge is negative 2 microcoulombs. Microcoulombs is just 10 to the negative 6. And I realized I didn't tell you what K was. I just did. So K, well, I told you it's a constant, but not the value of it, which you actually need to solve the problems. So quickly, let me run through that. It's equal to 8.99, or approximately 9, times 10 to the power of 9. Not negative 9. Like, the gravitational constant is very small. It's just positive 9. Times, and the unit is Newton times meter squared over Coulomb squared. So use that in your calculations, or you can use the value of epsilon naught, which you can find from K is just 1 over 4 pi epsilon naught. But I would suggest using this because it's just simpler. Okay. So we know that the electric field caused by 1 and 3 are going to be equal to each other because they're the same distance away from the point and they have the same charge, which is negative 5 microcoulombs. In this case, it's equal to E3, which is KQ over R squared. Only 1 Q because it's the electric field. And K we know is 8.99 times 10 to the power of 9. Q is, it's 5 times 10 to the power of negative 6 because micro is negative 6. And the distance is 10 centimeters, which is 0.1 meters. And so you plug all that into this formula, you get 4.49 times 10 to the power of 6 newtons per coulomb. That's the unit for electric field. Now, again, this would be Let's see. So if since it's electric field, we assume P is a positive test charge. That means it's going to be an attractive. So it's going to be going towards this way, because all of these are negative charges. Now that is the total value of the E1 and E3. But since they are the same distance away in different directions, the vertical, I guess, component cancels out because they're the same way. It's just the horizontal component that matters, which I'll talk about in a little bit. But first, let's calculate the electric field due to point 2. That is also kq over r squared. In this case, k is again 8.99 times 10 to the power of 9. Q is this time 2 times 10 to the power of negative 6 coulombs. And r, the distance between them, is 0.06 meters. It's 6 centimeters, so 0.06 meters. Plugging all that in, 4.99 times 10 to the power of 6 newtons per coulomb. So it's very similar. The charge difference and the distance difference kind of cancel each other out here, but it's not exactly the same. All right, now to actually get the total, it's going to be, for EY, which is what I was talking about earlier, E1Y and E2Y and E3Y, you add them up, all as vectors. E2Y doesn't exist because it's just moving in the x direction. E1Y and E3Y are the same in opposite directions, so this entire thing is 0, kind of like what I was saying before. EX is different. It's E1X plus E2x plus E3x. And that's just E2 is that we found earlier. It only has an x component, so that's just E2. And then E1x and E3x are the same, so it's going to be 2 times E1, it doesn't matter, E1 or E3, times the cosine of the angle. Now, it's a 6, 8, 10 triangle, which is just a derivative of the 3, 4, 5 triangle. And you would want to use trigonometric ratios to calculate the angle between them, but that's just going to be 53.1 degrees. Alternatively, you don't need to calculate the angle between them because you already got the ratios, so you can just use that ratio instead of cosine of inverse cosine of blah, blah, blah. It doesn't really matter though. You just use this and then you use that right triangle to find out what the x is. It's just trig. We've done this multiple times before in physics. And so you add all this up, you're going to get 1.04 times 10 to the power of 7 newtons per coulomb. So that's going to be your answer. That's going to be the magnitude of the electric field. What is the direction? That's just going to be towards the charges, because they're all negative, and you assume P is a positive test charge. All right, that was our first question over there. Moving on to 53. So this is kind of a problem I was talking about earlier, where it's a continuous charge distribution. You got a ring-shaped conductor, and this is the x-axis. You got a point on the x-axis. So the radius is 2.5 centimeters. The charge is 0.125 nanocoulombs. So nano is times 10 to the negative 9. In this unit, we're going to be talking a lot about those tiny, tiny units, because, like I said, 1 coulomb is a lot of charge. Point P is 40 centimeters away. Okay, so first let's actually derive a formula for the electric field due to a ring without any of the numbers, just with the symbols. That's going to be pretty interesting, and you're probably going to have to do that on the test. And so I'll just show you for a ring. It could be a different shape for you, but I'll just show you the general process. So you want to find out what E is, but each point of the ring is different. It's a continuous charge distribution. And so what you do is you use calculus a bit. You take a small section of the ring, ds, where s is like the length around the ring. So ds is a small infinitesimal segment of the ring. And let's calculate the linear charge density of the ring. So that basically is charge over length. In this case, length is circumference. So it's going to be q over 2 pi a. And that's going to help us because now we know that the charge over a small point ds is, charge is equal to the charge density times 2 pi a, where a is the entire, or 2 pi a is the entire circumference. So an infinitesimal point, a segment on the surface would be just ds. We said that before. ds is the length of the segment on that surface. And so dq, that tiny portion of charge that corresponds to ds is equal to lambda times ds, which is very useful for us. What does that help us do? Well, for that ds, you got dE, the infinitesimal portion of the electric field caused by that small segment. And that's equal to kq over r squared. What are q and r squared in this case? Q is dq, because that's just the charge of that segment. What's r? Well, r is going to be, it's actually going to be Pythagorean theorem again. So we got x, let's say, is the distance between the center of the ring and the point, and a is the radius. So r is going to be equal to square root of x squared plus a squared. But since it's r squared, it's going to be just x squared plus a squared down in this denominator here. But if you have a point up here and you have a point down here, the vertical components are going to be negligible, or they're going to cancel out. Similarly, if you have a point here and a point there, the z components are going to cancel off. So it's always just going to be pointing in this direction, because there's always going to be points on opposite sides that cancel out with each other. And so that means that we want the x component of the electric field, dex, is equal to dE times cosine of alpha, where alpha is the angle. Now, we already know this is a right triangle. So what is cosine of alpha? Alpha, well, that's adjacent over hypotenuse, which is x over r. So it's equal to k dq over x squared plus a squared times x over r. R is square root of x squared plus a squared. So what that basically tells us is the dex is equal to k times x times dq over x squared plus a squared to the power of 3 halves, because that's to the power of 1 to the power of half, adding it together to the power of 3 halves. We can simplify this a little bit, because we know that dq is equal to lambda times ds, and so you can split that dq into lambda times ds. You get dex is equal to k times x over x squared plus a squared, and then you also have that lambda and a ds over here. Now what we can do is integrate both sides of this expression. We got integral with respect to dE and an integral with respect to ds. That basically tells us electric field is equal to the integral of this. Now, I don't think they expect you to know what the integral of, oh, I forgot the 3 halves. Yeah, that 3 halves really messes stuff up. I think what they say is they use an integral table, which we don't really use anymore. You can use your calculator to integrate this, and they're probably not going to make you integrate this anyway. But the integral you get is just equal to k times lambda x over x squared plus a squared. Oh, wait, I forgot. Never mind. You don't have to integrate all that, because none of these depend on s, actually. So you just take all those out of the integral. So this is all out of the integral, and just integral of ds, which is just the entire surface, circumference. So that's just going to be 2 pi a. And we know lambda times 2 pi a is q, and so the electric field is equal to k times qx over x squared plus a squared to the power of 3 halves. So that's our formula for the electric field of a ring. And so we can just plug in our values. I'm going to have to erase a little bit of this up here probably to plug it in. It's asking for electric field is equal to k, which is 8.99 times 10 to the power of 9. Q is 0.125 nanocoulombs, so it's even smaller than, it's like 0.125 times 10 to the power of negative 9. X is 40 centimeters, so it's 0.4. Over x squared, again x, a squared to the power of 3 halves. A is 0.025 meters, because it's 2.5 centimeters. You plug all that in, you're actually going to get 7.0 newtons per coulomb, which is pretty nice. And what is the direction of that? Well, assuming this is it is a positive test charge, right? Because it's an electric field, we assume it's a positive test charge, and this is a positive ring. It's going to repel away, so it's going to be a positive 7. Assuming this is the origin and that's the x-axis, it's going to be positive 7 newtons per coulomb, and that's your electric field. For force, you just multiply it by electric field is equal to force over the charge of the test charge. In this case, the test charge is negative 2.5 nanocoulombs. So this is going to be towards, because it's a negative now. And so you just you solve for force is equal to electric field times charge. So it's 7 times 2.5 times 10 to the power of negative 6 because it's micro. And so you're going to get 1.75 times 10 to the power of negative 5 newtons as your force. And the direction, well, in this case, it's asking for the force on the ring. And so this would have been negative because if it was on the point charge, because it would have been attracted towards, which is in the negative x direction. But since it's asking about on the ring, it's going to be attracted towards the point, which is positive again. And so it's going to be 1.75 times 10 to the power of negative 5 newtons. So that was Newton's third law, by the way, that we used there. All right. So that was a pretty complicated problem, one of the most complicated problems we'll see in this subunit because it has to do a lot of calculus. This last one we have over here is calculating, it's using a dipole and it's calculating torque and stuff for that. First things first is calculating the force that this charge exerts on the dipole. How would you do that? Coulomb's law. You would do F1y, because all we care about is the y component. The x components don't really matter in this case. So F1 is equal to KQ1Q2 over R squared. K is 8.99 times 10 to the power of 9. Q1 is 5 times 10 to the power of negative 6, because it's 5 microcoulombs. You got 10 times 10 to the negative 6, and you got 0.02 meters as your distance between them. So that's going to be 1.124 times 10 to the power of 3 newtons. For F1y, which is just this portion, you get negative F1 sine of the angle between them. And the angle between them, you can use trig ratios because you know this. It's just a big right triangle over here, or you can just use this one. It's the same right triangle. And so you're going to get negative 842.6 newtons. Do the same thing for F2, and you're going to get F2y is also going to be negative 842.6 newtons, because this is like charges, and so they're going to repel each other, and so it'll be in the same direction. So the total net force in the y direction is going to be the sum of them, which is about negative 1680 newtons in that positive direction up there. Well, not positive direction, as in, well, it would still be a negative, but it's upwards. That's because the x components cancel. From the negative charge, it goes up. From the positive charge, it goes down. They cancel each other. For part B, it says, for an axis perpendicular to the line conducting, so this basically, that is the axis, find the torque exerted on the dipole. So torque we know is the dipole moment times, in this case we actually don't know the dipole moment, so it won't really be helpful, but we could calculate the dipole moment because it's Q times D. And what that tells us, Q we know is 5 microcoulombs, and D is 3 centimeters. So we can do that. And we actually don't know electric field, which we could calculate. There's an easier way to do that, though, and it's just the regular old formula for torque, which is force times like the distance of the distance perpendicular. And so in this case, that's going to be, we're going to use the x component of the force this time. And so F1x is going to be equal to this times cosine of that same angle. That's going to give us 743.1 newtons. And the torque is equal to force times the distance, which is this right here. I can't read that anymore. Well, we don't really know that. We just know this is 3 centimeters. And so the perpendicular line would be this, half of that. So it's going to be 1.5 centimeters or 0.015 meters, but multiplied by 2 because there's 2 parts of the dipole. And so all that together, 22.3 Newton times meters. What direction will it be? Well, like I said, this one will be repelled away. This one will be attracted towards, and so that is a total of a clockwise rotation. So that's your answer. 22.3 Newton meters clockwise. All right. And if you can believe it, that's just for the first part, which is electric field and electric charge. We still got two more parts, which is flux, Gauss law, and electric potential. For flux, this is a simple conceptual problem, I think. Well, not really conceptual. You still have to do some calculations. But the gist of it, what I wanted to get out of this is conceptual. This three small spheres carry charges, 4 nanocoulombs, negative 7.8 nanocoulombs, and 2.4 nanocoulombs. Find the net electric flux through each of the following closed surfaces. Okay, so for surface 1 is this. All we care about is the charges enclosed. The electric flux is equal to enclosed charge over epsilon naught. So all we want even is the enclosed charge. Anything outside is not enclosed. It goes through both sides of the surface, and so it's not part of electric flux. And so in this case, enclosed charge is just 4 times 10 to the power of negative 9 coulombs, nanocoulombs, divided by epsilon naught. And epsilon naught you can calculate because you know K is 8.99 times 10 to the power of 9. That's equal to 1 over 4 pi epsilon naught. So solving for epsilon naught, you would get epsilon naught is equal to K 1 over 4 pi K. And so you would get approximately 8.85 times 10 to the power of negative 12 as your value for epsilon naught. And so you plug that in here, you're going to get 452 Newton times meter squared per coulomb is the unit for electric flux. That's just because that's coulomb up there, and you can find the units for epsilon naught again through the equation. Or you can just do electric field times area. Well, that's meter squared, that's newtons per coulomb, and so you get that. For S2, again, it's enclosed over epsilon naught. Enclosed this time is just Q2. And so that's negative 7.8 times 10 to the negative 9 over epsilon naught. So that's going to be negative 881 Newton times meter squared per coulomb. For S3, S3 here is both of these. So it has two charges. And so it's Q1 plus Q2. Since Q2 is negative, it'll just be 4 minus 7.8. Again, nanocoulombs. And so it's going to be negative 3.8 times 10 to the negative 9 coulombs as your charge, divided by epsilon naught, is negative 429 Newton times meter squared per coulomb. Another way you could have done that, 452 minus 881. Because all you care about is the charge. You don't care about how big it is or whatever. The fourth loop is this one right here. It has Q1 and Q3. You add this up, both are positive, so it totals up to about 6.4 nanocoulombs. 6.4 times 10 to the negative 9 divided by epsilon naught. So for the fourth one, it's going to be equal to 723 Newton times meter squared per coulomb. Finally, for the fifth one, it has all of them in it. And so Q1 plus Q2 plus Q3, 4 minus 7.8 plus 2.4 is going to be equal to negative 1.4 times 10 to the negative 9 coulombs divided by epsilon naught gives us negative 158 Newton times meter squared per coulomb. And yeah, that's it. For part F though, do they depend on how the charge is distributed over each small sphere? No, because all you care about is how much charge there is, not where the charge is. That's basically everything in this Gauss's law. Okay. This one is a bit trickier. It's a hollow conducting sphere. And so you got a sphere like that. Outer radius of 0.25 meters and an inner radius of 0.2 meters. And it has a uniform charge density of 6.37 times 10 to the negative 6 coulombs per meter squared. Now you got a charge of negative 0.5 microcoulombs inside the sphere. What is the new charge density? Okay, so before it was introduced, you can calculate the total charge as the charge density. So in this case, it's per meter squared, so it's sigma, times area. The area of a sphere, the surface area, is 4 pi r squared. And since it's a conductor, all the electrons are going to move wherever they want. And so all the charge is going to be distributed evenly around the outer surface, not the inner surface, the outer surface, because they want to be as far away from each other as possible. And so you use the outer radius here, capital R. So you know sigma is 6.37 times 10 to the negative 6 multiplied by 4 pi times 0.25 squared. You're going to get Q is equal to 5.0 times 10 to the negative 6 coulombs. That was the original charge on the outside of the sphere. But once you got negative 0.5 microcoulombs down here, the charge moves a little bit, because you got this negative charge here and you got a positive charge on the outer sphere. Part of the charge is going to come onto the inner surface, so it's equal to that of the random charge that was added. So you got 0.5 microcoulombs on the inner surface, and so what's left is just 5.0 times 10 to the negative 6 minus 0.5 times 10 to the negative 6. So the Q in the outer would be 4.5 times 10 to the negative 6 coulombs. That should be a coulomb over there. Now for the surface charge density, you just divide that by the area. Area we know is 4 pi r squared. We already know r is 0.25. And so sigma is going to be equal to approximately 5.73 times 10 to the negative 6 coulombs per meter squared. So it is going to decrease because some of the charge moved down to the inner surface. Calculate the strength of the electric field just outside the sphere. So over here, you can use Coulomb's law again. Or sorry, not Coulomb's law, Gauss's law. So that basically tells us, in this case, it's a constant electric field, at least for all the points around here. And so you don't really need to use the integral form. You can just do electric field times the area is equal to the electric flux, which is equal to Q over epsilon naught, which means electric field is equal to Q over epsilon naught times the area. Q we know is, it's the net charge that is enclosed. And since the negative 0.5 in the middle cancels with the positive 0.5 in this inner surface, the net charge is just whatever's on the outer surface, which is 4.5 times 10 to the negative 6 coulombs. So that's this Q over here. Area, we know, since it's just outside the outer edge of the sphere, it's again 4 pi r squared, the capital R. And we know epsilon naught. So you plug all that in, you're going to get an electric field of 6.47 times 10 to the power 5 newtons per coulomb. So that's your electric field. And then for the electric flux, through a spherical surface just inside the inner surface of the sphere. So that's right here. The only net charge that's enclosed is this negative 0.5 microcoulombs in there. So again, we use Gauss's law. This time, electric field is equal to, electric flux equals electric field times A, which is equal to Q enclosed over epsilon naught. We don't care about this part right now. It's just Q enclosed over epsilon naught. Q enclosed is negative 0.5 microcoulombs, and epsilon naught we know, and so you just get an electric flux, which is what we want, not electric field, of negative 5.65 times 10 to the power 4, and the units are Newton times meter squared per coulomb. And so that's your answer. That wasn't too bad. Moving on down here, this is a challenging problem because it's like a lot of calculus and stuff. And yeah, it's similar to, well, not similar to in terms of concepts, but in terms of like the math level of it, it's similar to that previous one we did with the ring. And I should probably erase this. Okay. So we got a non-uniform. We've only been dealing with uniform and symmetric distributions. This is non-uniform distribution. And so it's given by this piecewise function here. So if you have a value r, which is basically, in this case, the radius of the sphere, and up till the radius r, you got a volume charge density of some constant rho naught times 1 minus 4r over 3 capital R. And then outside it's 0, which basically tells us the edge of the sphere is capital R. Find the total charge contained. Well, the total charge contained is basically just rho times v, but it's not that simple because rho is not uniform. If it was a value, it would just be rho times v. But what do you do when you multiply stuff and one of them is not a constant? Yeah, you use integrals. Q is equal to the integral of rho with respect to r times dv. Now we don't have anything with respect to dv, so we want to get it to dr. This is a function in terms of r. So what is dv in terms of r? Well, we know the volume of a sphere is 4/3 pi r cubed. So implicit differentiation, you just differentiate both sides. dv is equal to, bring the 3 down, it's 4 pi r squared dr. And so you plug that up there. It's equal to rho of r times 4 pi r squared dr. So you can take out the 4 pi. We are going from 0 to infinity, but we know that after it reaches r, it's 0. And so all you care about is to r. So that becomes, the 4 pi goes outside. It's 0 to r of rho of r, which is rho naught. Again, the rho naught goes outside. It's 1 minus 4r over 3 capital R times r squared. Don't forget this r squared here. And so it just becomes r squared minus 4 lowercase r squared over 3 capital R dr. And so you can, oh, sorry, this should be r cubed, because r squared times r is r cubed. And you would calculate this integral. I'm not going to show you that work because that's calculus. It's not that hard because this is just power rule for both of these, basically. You're going to get q is equal to 4 pi rho naught, that was outside, times r cubed, r cubed over 3, minus 4 over 3r, I should probably rephrase that. It's r to the 4th over 3r, capital R, from r to 0. When it's 0, it doesn't, all of this is 0. But when it's r, it becomes r cubed over 3 minus r to the power 4 over 3r. Well, one of the r's cancels. It's just r cubed over 3 minus r cubed over 3, which is 0. And so that means the total charge enclosed is 0. That's huge. Your answer is 0 coulombs. I'm going to have to erase this for the next part, because we took too much space there. But it's saying, obtain an expression for the electric field in the region r is greater than or equal to capital R. So we know that the electric field out here is Gauss's law. Electric field times the area is equal to q over enclosed over epsilon naught. Well, q enclosed is 0. We just found out that the total charge is 0, which means the electric field has to be 0, because area is not 0. If this entire thing is 0, that means the electric field has to be 0. So that means electric field equals 0. For C, obtain an expression for the electric field inside the region. Well, again, we use calculus for that. It's q enclosed over epsilon naught. And so it's the exact same integral. It's 4 pi rho naught. 4 pi times the integral, this time from 0 to lowercase r, because it's a set amount, not that uppercase r before, times rho. We can't really use r again because that's up here, so I'm just going to use r prime times r prime squared dr prime. This is the integral from before. You integrated the same way by taking out substituting the function for this, and it's going to be the exact same thing. It's rho naught, 4 pi rho naught, but this time over 4 pi epsilon naught, and so the 4 pi's cancel off, and it's times 1 over r squared times r cubed over 3 minus r to the power 4 over 3r. That all comes after we substitute in the r for r prime. And so it just becomes rho naught over 3 epsilon naught, because of this 3 that gets distributed out, times r times 1 minus r over r. So that's your expression. It's pretty complicated, but it's just calculus to get from one step to another. To graph it, this is a parabola because there's an r and an r here. It's just going to look something like this. You would, again, it's math. This is a physics class, so I'm just going to skip like the mathy parts, which you should get from calculus, and this from algebra probably, because it's just graphing r times 1 minus r, basically. And you find the value of r at which the electric field is maximum. So the electric field is maximum when the derivative of the electric field is 0. We know that from calculus. And so you just take the derivative of this with respect to r, and you set it equal to 0. What is the derivative of dE of E? This is going to stay the same. And this becomes r minus, here, let me erase this. It becomes rho naught over 3 epsilon naught times r minus rho naught over 3 epsilon naught times r over r, because you just distributed it out. So with respect to r, this just becomes rho naught over 3 epsilon naught minus the same thing. sorry, this should be r squared. So now you bring down a 2, and you're just left with r up here. And so, again, you can factor it out. Rho naught over 3 epsilon naught times 1 minus 2 over r is basically what it is. And you want that to be equal to 0, so you have, 2r over r. R has to be equal to half of capital R, because then you get 1 minus 2r over capital R equals 0, so 2r over capital R equals 1, so 2r equals capital R equals capital R over 2, 1/2 r. And so that is basically it. That is your answer. And find the value of the maximum field. You just plug it back into this equation, and you get an answer for that. All right. Almost done here. Just one last subunit, which is electric potential. And we got 3 problems for that. This first one is an equilateral triangle where you got 3 charges. 2 of the point charges are identical and have a charge q, and the distance between them is d, d, d. If 0 net work is required to place the 3 charges at the corners of the triangle, what must the value of the third charge be? So let's say this is QC, the value of the third charge. We know work is equal to negative change in potential energy. And that's just equal to U1 minus U2, where you're moving from 1 to 2. And so U1 equals 0 because it's infinitely far away. And we know that electric potential energy at infinitely far away is 0. As for U2, it's equal to, you have to calculate all the potential energy pairs. So between, let's say this is A, B, and C, between A and B is going to be KQ squared over R. In this case, R is D. Plus, between A and C is KQ times QC over D. And then between B and C is the same thing. So this just becomes 2 times that. Which means that you can take out a K over D times, K over D times Q squared plus 2Q QC. Since it's U1 minus U2, it just becomes negative of this is equal to the work, which is equal to 0. And so that means this is equal to 0. So Q squared plus 2Q times QC equals 0, which means Q plus 2QC equals 0. And so QC is equal to negative half of Q, for that equation to make sense. And you can also make sure the sign is right, because if it was all positive charge, they would repel each other. Since it's all negative, since it's 1 negative and 2 positive, it makes sense. This question over here, you got a positive charge fixed at point x equals 0, y equals 0, and a negative charge at a comma 0. So both on the x-axis. So this is q, this is negative 2q. Show the positions of the charges on a diagram. I just did that. And the distance between them is a. Derive an expression for the potential, not potential energy, potential V at points on the x-axis as a function of the coordinate x. All right, let's make different cases. First of all, if x is greater than a, the potential from this point is equal to KQ over D, the distance, or R, and in this case, R is X, because it's this far away point X. It's just distance from the origin, so that's that. But for the potential from this point, it becomes minus 2KQ, the 2 because it's twice the charge, over x minus a, because there's this a distance, and that's x. So the distance between these has to be x minus a. And so you can combine that just by, it's just algebra combining them. It's negative kq times x plus a over x times x minus a. So that's your expression for x is greater than a. For 0 is less than x is less than a, that's between these two, This time it's kq over x minus 2kq over a minus x, because in this case here, the distance between them is a minus x. If it was x minus a, it would be negative, which we don't want. It has to be a minus x. And so combining these together, you get kq times 3x minus a over x times x minus a. Again, just algebra. For x is less than 0, this time it's going to be negative kq over x, because it's all the way on this side. And the reason why it's negative is because x itself is negative, and we want a positive answer, so you have to take the negative of a negative to get the positive. Again, this has to be plus because of the same reason. 2kq over x minus a, and combining them is kq times x plus a over x times x minus a. Same thing as that first expression here, but negative of that, so it becomes positive. Yeah, and if you want a general expression, it's going to be k times q over absolute value of x, absolute value to indicate that even if it's negative, it's positive, minus 2q times absolute value of x minus a, especially for this part where it has to be a minus x for it to remain positive. So yeah, that's your answer. Part C, at which positions is v equals 0? Well, you just set this equal to 0. You get q over absolute value of x minus 2q over absolute value of x minus a is equal to 0. So it's just dividing by q. It's 1 over absolute value of x is equal to 2 over absolute value of x minus a. And you just have to solve for a. You can take different cases, like in x is less than 0, you can solve for it. And this, you can solve for it, you'll get a solution. Here, you won't get a solution. But if you do solve for it, when you do take the cases, you can get rid of the absolute value signs, which makes it much easier to solve. I'll do x is less than 0 for you. That since x is less than 0, it becomes negative 1 over x is equal to 2 over a minus x. And so multiplying both sides, a minus x times negative 1 gives you x minus a is equal to 2x. And so x, moving the x to one side, x equals negative a. So that's one solution. For 0 is less than x is less than a, it is 1 over x. This time it's positive, but x minus a would be negative, so it becomes 2 over a minus x. And multiplying it out, a minus x is equal to 2x, so 3x equals a, which means x is equal to 8/3. And that is also within the region. You can do it for x is greater than a, but you're not going to get a solution for that, so I won't bother. Graph v at points on the x-axis is a function of x in the range from negative 2a to positive 2a. So it's going to look a bit like this. Between negative 2a and 0, it's going to look like this, like an inverse function. Between a and 2a, it'll also look like an inverse function, but in this quadrant. And in the middle, it would look like this. And that's because you're going from close to one point to close to another, and so it's kind of like a mix between the graphs. If you actually wanted to graph it by hand, you would have to like actually come up with points to plot, or you could just use a graphing calculator or something like that. Finally, E, what is the answer to part B become when x is much, much greater than a? Part B was this. Well, yeah, I think part B was all of this. And so when x is much, much greater than a, that would be in this case. And that means that x minus a is roughly equal to x itself, because x is much, much greater than a. So you're going to get negative kq times x plus a is also going to be around x. So it's x over x times x, which is x squared. So it's just negative kq over x as your answer. All right. So it's basically like, hey, there's just one point that is charged negative q, because that means that the distance between them is negligible. All right, last question. We're almost done with this video, and I know it's a very long one, so glad you're still here. You got a very long wire carrying a uniform linear charge density. So this one is actually a pretty long question. It's a lot of math and derivations, but don't worry, we can get through it. You got a very long wire, uniform linear charge density lambda. First of all, we want to try to find an equation for the electric field in terms of lambda, and then you want the electric potential in terms of lambda. Because we got voltmeters, you're measuring potential difference, which is just the change in electric potential. So for a long line of charge, first let's calculate the electric field. Let's use Gauss's law for that because that makes stuff much easier. We know this is equal to E times A, which is equal to Q over epsilon naught. A is, so you can treat a Gaussian surface, which is just a cylinder around here. In this case, through the faces, it gets cancelled out, but through this side, it goes out. And so your area is going to be the surface area, the lateral surface area of the cylinder. So just this side, not the faces. And so this circle is going to be 2 pi r times this length L. So 2 pi r L will be your area. Q is going to be equal to lambda times L, because lambda itself is equal to Q over L. You just solve for Q. So you get E times 2 pi r L is equal to lambda L over epsilon naught. L's cancel, and you're going to get E, 2 pi r E is equal to lambda over epsilon naught. And so E is equal to lambda over 2 pi r epsilon naught. So that's for electric field. I'm going to erase the derivation of this so we can solve for potential. What is the formula for potential? The change in potential from A to B is equal to the integral from A to B of electric field times dl. In this case, we can just treat it as E times dr because electric field is constant. It's uniform. And we know the formula for that is this. We can take out a lambda 2 pi epsilon naught. So it's lambda over 2 pi epsilon naught times integral from A to B of 1 over r dr. And integral of 1 over r is ln of r. Since it's from A to B, you treat this as from B to A, which is ln of B minus ln of A. In this case, radius is always positive, so we can get rid of this absolute value. And properties of logarithms tell us this is just ln of B over A. And in this case, B and A are points, and so it would just be the radius at B and radius at A, which means that the change in potential is equal to what was it? Lambda over 2 pi epsilon naught times ln of RB over RA. So yeah, that's useful to know. Now we get into the actual solving of the problem, which is you got a voltmeter, and one end is 2.5 centimeters above, and the other is 1 centimeter farther than that. And so in this case, RB will be 3.5, RA will be 2.5, and so you just solve for lambda with that. You know delta V is 575 volts is equal to lambda over 2 pi epsilon naught. We know what all those are. Well, we don't know what lambda is. That's what we're trying to find. Times ln of 3.5 centimeters over 2.5. In this case, we don't have to convert to meters because it's a ratio. The centimeters cancel off. It's the same ratio. And so you just solve for lambda. You're going to get lambda is equal to 9.49 times 10 to the negative 8 coulombs per meter because it is linear surface density. Now, if you place one probe at 3.5 and the other one at 4.5, will the voltmeter still read 575? Well, no, because we know that as radius increases, it gets weaker. And so if you have this and that, this 1 centimeter is not the same as this 1 centimeter. And so it's going to be less than 575. And finally, part C, if you place both probes at 3.5 centimeters from the wire, but a different horizontal distance, what will the voltmeter read? Well, the horizontal distance doesn't matter. It's just the distance from the wire. So RB over RA would be 1. And ln of 1 is 0. And so the change in potential, the potential difference, would be equal to 0. And so that's what it would read, 0 volts. And that's it for this video. We covered all of electrostatics, the entire first unit of E&M. So welcome to E&M. It's just the first unit. Then we're going to learn about capacitors and circuits, and then we're going to get into magnetism. So it's going to be a pretty long journey for this one. So good luck for your test and the AP exam, and I'll see you in our next video.